Hey guys, welcome back to AlgoYogi, and we are doing binary search. And our next problem in the list is valid perfect square. So let's go to the LeetCode and give it a read. So given a positive integer num, return true if num is a perfect square or false otherwise. And if you are a cool kid, technology kid, you would know what a perfect square is. But if you don't, then let's read the definition here. So a perfect square is an integer that is square of an integer. Okay, integer means -1, -2, 1, 2, 3, no decimals. Okay, in other words, it is the product of some integer with itself. So some integer k into k square, if that makes the number n, what the fuck is that? Oh my god, they just named the number num. Yes, so if it is equal to num, then k square equals to num. That means our num is a perfect square where k is an integer. All right, so let's find out if num is a perfect square. In this case, you can see 16 is a perfect square because it's a square of 4. So 4, if 4 is k, 4 into 4 is equal to 16. 16's under root makes 4. 4 is an integer. Bam! Perfect square. All right, what about 14? It is not, because there is no integer, whose square basically is 14. So let's understand how we're going to find out our answer. Valid perfect square. And negative integers also have square, but let's start with, because negative number into negative number makes a positive one. So basically what I'm saying is 0's square is 0. All right, because 0 into 0 is 0. Then 1's square is 1, 2's square is 4, and 3's square is 9, 4's square is 16. Okay, so what are the perfect squares? This 16 is a perfect square, 9 is a perfect square, 4 is a perfect square, 1 is a perfect square, 0 is a perfect square. What is not a perfect square? Any other number, any other integer, I would say, between these numbers. Basically 3 or 5 or 7 or 6 and blah blah blah. So we are given numbers like this, and we gotta tell if they are perfect squares or not. So for example, in our very first example, we were given 16, which is a perfect valid perfect square, and that is because 16 is equal to 4 to the power 2, where 4 is our k is an integer. All right, so second example was 14. If you take under root of 14, then you can't get a valid integer. So that means it is not a perfect square. So we just return false. So what does that mean? How are we going to find out if something is a perfect square? So now we understand that. So let's use that knowledge to find out if our given num is a perfect square. So if, let's say, our given num is 16, that means what? If num is 16, it's basically under root of 16. So there should be a number between, let's say, 1 to 16, let's say k, where that k is basically k square is equal to 16. This is our condition. So we are trying to find out this k, my guys. And how we can find out that k is basically, how about we run a loop? We run a loop starting at basically I equals to 1 to I equals to num, right? And here we check if I into I is equals to num, then just return true. Otherwise you come out of this loop and you return false. All right, but the thing is, its time complexity would be basically, you know, like when you reach this k, that means you reached under root of n, right? Because that would be the number that's equal to under root of n, which is k square equals to n. N is our num. Perfect. We are mathematician, guys. Okay, but now you understand like why our time complexity would be under root big of n, right? So under root n, like big of under root n. Sorry, I don't know. I'm just, you know, blabbering whatsoever. Can we do better, guys? Yes, that's what binary search is about. Rather than iterating from 1 to num, how about we make use of, by the way, binary search. So we start at 1, blah blah blah, there will be some k which will basically be whose square will be equal to 16, or this could get, like, let's say this right now it's 16, but it could have been 17, and we would still try to find where this k square would be equal to 17. So what we want to do is we'll have our pointers, left pointer pointing to 1, right pointer pointing to 17, and then we are finding the mid will point to some number, you know, and then we will basically try to check if mid into mid or mid square, that's a better way of calling it. So mid square, is it equal to 17? If it is, then return basically true. Otherwise check if mid square is lesser than your num. If it is lesser than your num, then our L basically needs to go up so that we can find a, you know, we can find a higher mid whose square would actually be equal to like either close to 17 or even if not equal to, right? Because we are trying to get to a higher integer than k if mid square was less than basically num. If it was a smaller than num, that means we will try to bring our right pointer to basically mid minus 1. All right, so those will be our conditions, and I think once if our basically left becomes greater than our r, then we break out of that and then basically return false. Otherwise we will just keep appropriately moving these left and right pointers, either left to mid plus 1 or right to mid minus 1. So let's code up the solution. I think these are like easy problems, so I guess we shouldn't have any issues understanding, you know, the logic behind it. So let's write it down. All right, so what I'm gonna do is, by the way, the brute force approach would be just like using a for loop, start at 1, keep looping, and whenever you come across I into I equals to num, then break out, return true. Otherwise, like go until n num, and then and I'm sure you wouldn't find their answer, and then you just return false. So that would be brute force, whose time complexity would be you know, under root n. But better solution, binary search, left and right pointing to basically 1 and num. Sorry, not nums. I don't know, I was like not very happy they named the number num. They should have named it n, because usually they call the, maybe, I don't know, it's okay. So while left is less than or equals to r, find the mid, which will be left plus right, and divided by 2 so that we get the integer. If mid into mid is greater than num, that means what? Our right needs to come down to mid minus 1. If mid into mid is basically smaller than num, then we can just take our left pointer to basically mid plus 1. All right, otherwise there are 3 cases, guys, only. If this is greater than nums or lesser than nums, or it's actually equal to num, that means we return true, that we found that there was a number k whose square, perfect square by the way, because we are taking the integer division here, perfect square was equal to num. So that means num is a perfect square. If you under root num, that means you find a k and k square is equal to num, so you return true. Otherwise this condition must have happened and you never came across any valid k where whose square was basically equal to num, so you just return false, mere bhai, false. All right, so and its time complexity would be log n. Previous one was root n. Okay, so I think I don't see any issues right now, so maybe let's try to zoom out and run it on our examples. Nice, I like it 100%. Okay, time complexity, we can write it down. I'm trying to be funny, but I see that I'm not funny, and that's what she said. She didn't say I'm not funny. I think I'm funny. No one is gaslighting me. Okay, big of log n, that is the time complexity, and I can prove it, by the way, because you have these 2 pointers pointing to left and right, and each time you decide where your answer is going to be and you find out the middle. So every time you're just bringing your input to basically n by 2, so n by 2, n by 2, n by 2, until your basically target, or size of your input becomes 1. That means n to the n by 2 to the power k equals to 1. That means 2 to the power k equals to n. Take log both sides, so k equals to log n base 2, by the way. So that is how you find out that your time complexity is log n. What is space complexity, guys? You know what I'm saying? You know what I'm saying? So hard to act cool, man. Really hard. Life is hard. Is life hard? I think it's not really hard. It's like there is so much going on. I think we got confused somewhere along the time that and we were just people are doing something, but nobody actually know. I don't know what I'm doing here. It's just I'm doing something. I'm writing LeetCode solution. What the fuck is going on? 250 years ago, nobody knew what this shit is. Anyway, it's fun. It is not fun. It is fun. Okay. Space complexity is constant, which is because we didn't use any extra memory. And let's go to AlgoYogi, the website that we built together to track our problems, the problems we're solving. Mark it solved, and until then, see you guys later. Until then, bye-bye. That's how the video started. That's how it ends. And I just bought a little gift for me. This is me, guys. Yeah, just coding monkey. Initially I wanted to name this code monkey, but that's taken. Somebody took that. Okay, anyway, bye bye.